Greetings, I am Zyril F. Fernandez from Team Terbium, and along with my members Tricia Luis I. Francisco, Sophie Miles F. Mariano, Albert R. Sobile, and James Vincent C. Santiago, join us as we delve into the dynamic world of chemical kinetics. As seen in this slide, this comprehensive discussion is going to be divided into 5 parts. Without further ado, let's start with the introduction to chemical kinetics and the rate of reaction. Kinetics is a word that suggests movement or change. Basically, chemical kinetics answers the question, how fast does a reaction proceed? It is the rate of a reaction, which is the change in the concentration of a reactant or a product with time. We know that any reactions are represented by this general equation. This tells us that during the course of a reaction, reactants are consumed or their concentrations decrease while products are formed or their concentrations increase. In general, it is more convenient to express the reaction rate in terms of the change in concentration with time as shown in this figure. Thus, we can express the rate in this equation. Here, it is important to take note that because the concentration of A decreases during the time interval, it is a negative quantity, unlike B, which is increasing with time. We can measure rates of reaction in different ways, but any method will still involve measuring the changing concentration of a substance, either through spectroscopy, electrical conductance, or pressure measurement. Let's have an example by considering the reaction of molecular bromine and formic acid. In this illustration, visually, we can already say that from left to right, the decrease in bromine concentration as time passes shows up as a loss of color. But let us try using the equation earlier to compute its average rate. The average rate is the change in concentration over a selected period of time. Using the data provided in the table, we can calculate the average rate over the first 50-second time interval as 3.80 times 10 raised to negative 5 molarity per second. For the 100-second interval, we have 3.54 times 10 raised to negative 5 molarity per second. Now that we have the average reaction rate, we can calculate it over shorter and shorter intervals to get what we call the instantaneous rate. The instantaneous rate is the rate at a particular time. It is determined by finding the slope of the tangent to the concentration versus time curve at that time. Shown in this graph are the instantaneous rates of the reaction at 100, 200, and 300 seconds given by the slopes of the tangents. Now, let us observe this graph. This is the plot of rate versus molecular bromine concentration for the reaction. The straight line relationship here shows that the rate of reaction is directly proportional to the concentration. This can be expressed as the shown equation, where the term K is known as the rate constant. The rate constant is a constant of proportionality between the reaction rate and the concentration of the reactant. By still using the data in this table, here is an example of how to compute the rate constant. Taking the data for the 50 seconds, K is equal to the rate over the concentration of the molecular bromine, and the answer is 3.49 times 10 raised to negative 3 per second. Now, let us have an example of a calculation using the rate expression. Let us consider this reaction shown in this slide. Here, the rate is expressed as this because we can see that 2 moles of A disappear for each mole of B that forms. So, the rate at which B forms is 1/2 the rate at which A disappears. Here is another example. Suppose that at a particular moment during the reaction, molecular oxygen is reacting at a rate of 0.024 molarity per second. A. At what rate is dinitrogen pentoxide being formed? B. At what rate is nitrogen dioxide reacting? To calculate, we first need to express the rate of the reaction in terms of their stoichiometric coefficients. Now, by taking into consideration the rate expression and the value at which molecular oxygen is reacting, A is equal to 0.048 molarity per second, while B is equal to negative 0.096 molarity per second.
So far, we have learned that the rate of reaction is proportional to the concentration of reactants, and the proportionality constant K is called the rate constant. The rate law expresses the relationship between the rate of reaction, the rate constant, and the concentrations of the reactants raised to some power. For the general reaction shown here, the rate law takes the form rate equals the rate constant times the concentration of reactant A raised to the power of X times the concentration of reactant B raised to the power of Y. The exponents x and y specify the relationships between the concentrations of reactant A and B and the reaction rate. When added together, they give us the overall reaction order, defined as the sum of the powers to which all reactant concentrations appearing in the rate law are raised. Now that we have learned the equation to be used in the rate law, let's apply it to solve the sample problem here. Consider the reaction. A reacts with B to produce products. From the following data obtained at a certain temperature, we need to determine the order of the reaction and calculate the rate constant. In the table shown here, the concentrations of reactants A and B in three trials are provided along there with their respective rates. To begin, let's solve for the order of the reaction with respect to the concentration of reactant A. In experiments 1 and 3, the concentration of reactant B is kept constant while the concentration of reactant A is varied. We will choose these experiments and apply them to the equation of the rate law as shown here. Now, let's substitute all the values and cancel the rate constant and the concentration of reactant B raised to the power of y, since applying the quotient rule for exponents results in it being equal to 1. Next, we need to isolate x, so we apply the power rule of logarithms, divide both sides by the logarithm base 10 of the ratio of 3 over 1.50, and we obtain the value of x as 1, indicating that the reaction is first order. So, the same steps are used to determine the order of the reaction with respect to the concentration of reactant B. Here, we choose experiments 1 and 2, where the concentration of A is kept constant, but the concentration of B is varied. Applying the rate law equation and substituting the values, we obtain a y value of 0, indicating that the reaction is zero order with respect to B. By adding the x and y values, we get the overall order of the reaction, which is equal to 1, indicating a first order overall reaction. And for the determination of the rate constant, all we need to do is rearrange the equation from the rate law and substitute the values using the data from any one of the experiments, as they all yield the same result. Ensure that you use the x and y values we obtained earlier for the order of reaction with respect to A and B. In this case, I chose the data from experiment 1 and obtained a rate constant value of 2.1 times 10 raised to negative 1 per second.
The zero-order reaction is a rare type of reaction in which the rate is constant throughout the reaction. Take the reaction reactant A produces products. The rate of the reaction is equal to the rate constant multiplied by the concentration of reactant A raised to 0. Mathematically, anything that is raised to 0 is equal to 1, and multiplying the rate constant by 1 is just the rate constant. From this, it can be concluded that the rate of reaction is not reliant on the initial concentration of the reactant. The zero-order reaction can be obtained using calculus. It shows that performing the integration, we get A sub t minus the initial concentration is equal to the negative rate constant multiplied by the quantity of t minus 0. We can rearrange the equation linearly, resulting to A sub t is equal to negative product of k and t plus the initial concentration. On the screen, we see the corresponding values of each component of the zero-order equation, which are A sub T is the concentration at time T. T is the time of reaction, K is the rate constant of reaction, A sub 0 is the initial concentration of reactant. Also, it is shown in the screen is the zero order graph, which has a negative slope.
Moving forward to the first order reaction, it is a reaction whose rate depends on the concentration of the reactant raised to the first power. In other words, a first order reaction is a chemical reaction in which the rate varies based on the changes in the concentration of only one of the reactants. Thus, the order of these reactions is equal to 1. A common example of a first-order reaction is radioactive decay because it depends solely on the concentration of a single reactant, the radioactive atom. There is no need for it to react with another substance for decay to occur. The first figure here illustrates the graphical representation of a first-order reaction where the concentration of the reactant A decreases with time. In the second figure, it is demonstrated that plotting the natural logarithm of the final concentration of reactant A against time results in a straight line. The slope of this line is equal to the negative rate constant and the y-intercept is equal to the natural logarithm of the initial concentration of reactant A. Therefore, the rate constant can be calculated from the slope of this plot. Moving forward to the derivation of a first-order reaction, the general form of a first-order reaction can be expressed as follows. Reactant A changes into products. The rate expression for such a reaction is given by the equation the rate is equal to the change in the concentration of the first-order reactant A in the time interval dt. The negative sign indicates that the concentration of A is decreasing with time. From the rate law, we also know that the rate is equal to the rate constant multiplied by the concentration of reactant A. To obtain the units of the rate constant for this rate law, we write the rate constant as the rate over the concentration of reactant A. The unit for the rate constant of a first-order reaction is per second. Combining the first two equations for the rate, we get the rate of disappearance of reactant A over time equals to the rate constant multiplied by the concentration of reactant A. Next, to remove the derivative from the denominator and move it to the numerator, divide both sides by dt. Then, divide both sides by -1 over the concentration of reactant A. By rearranging, we get the rate of change of the reaction of A with respect to the concentration of A is equal to the negative rate constant times the differential time. Next is the integration of this equation. Integrating it between the initial time of the reaction and any later time during the reaction results in the natural logarithm of the concentration of reactant A at a specific time minus the natural logarithm of the initial concentration of reactant A, which equals the negative rate constant times time. The equation can be rearranged as a linear equation where the y-intercept is equal to the slope of the line multiplied by the x-intercept. This is demonstrated here where the natural logarithm of the concentration of reactant A at a specific time equals the negative rate constant times time plus the natural logarithm of the initial concentration of reactant A.
Now we are on to another one, which is the second order reaction. A second order reaction is a reaction whose rate depends on the concentration of a reactant or the reactants. So what do I mean? A second-order reaction may be exhibited by a chemical reaction containing one reactant in which that one reactant is raised to the second power. But it can also be present in chemical reactions having two different reactants, each raised to the power of 1. So suppose a reaction is given by addition of the same reactant, A plus A, or simply 2A, to produce certain products. The rate of a second-order reaction for this equation can be written as rate is equals to the rate constant K multiplied by the concentration of A raised to the power of 2. But if there are two reactants in a chemical equation, or simply A plus B to produce certain products, the total rate of this reaction is written as rate is equals to rate constant K multiplied by the concentration of A raised to X multiplied by the concentration of B raised to Y, where X and Y in this equation each corresponds to the order of the given chemical reaction that when added gives the sum of 2. So for second order reactions, the unit of the rate constant is reciprocal molarity by reciprocal seconds. To get the second order reaction, we will use the reaction that is dependent on the concentration of a single reactant. But first remember that when time is equals to 0, we are starting with our initial concentration, and at some time t, it is equals to the concentration of A at some time t. So first, since we can write our rate expression in two forms, we are going to use that. So rate is equals to the negative change in concentration of A over change of time. Also, we have rate is equals to the rate constant K multiplied by the concentration of A raised to the second power. So using calculus, we can express this rate as instantaneous given by the reaction negative d concentration of A over dt is equals to K multiplied by concentration of A raised to 2. Rearrange the equation so that we can have like terms in one side of the equation, and we will be left with negative dA over concentration of A raised to 2 is equals to K dt. So we can then proceed with the integration of the equation. Using the same equation, we will integrate it from the initial concentration of A to concentration of A at some time t. Since K is a constant, we can also put it outside the integral sign so that we will left with the integration of dt from initial time to some time t. So using the power rule of integration, we are left with 1 over the concentration of A at some time t minus 1 over the initial concentration of A is equals to Kt. So rearranging the formula, we are left with 1 over concentration of A at time t equals to Kt plus 1 over initial concentration of A. So for the second order reaction, we have the plot of 1 over the concentration of A at some time t versus t, which gives a straight line with a slope of k and y-intercept of 1 over initial concentration of A, which is linear. And this is similar with our linear equation that we calculated a while ago, which is given by this equation, where again we have 1 over concentration of A at time t equals to negative Kt plus 1 over the initial concentration of A.
Presented in the screen is an example for the determination of the order of reaction. Given below is the gas phase decomposition of hydrogen iodide. What is the order of reaction? If you have an idea for solving this problem, you can pause the video. If not, you can take a guess. The strategy for this problem is to create a table with the concentration of hydrogen iodide, which is for zero order, the natural logarithm of concentration of hydrogen iodide for first order, and the reciprocal of the concentration of hydrogen iodide for the second order as a function of time. The values obtained will be used for graphing as y values against the x values, which is the time. Presented on the screen is how the graph of each values we obtained earlier looks like when plotted with the time. Graph A is zero order, graph B is first order, and graph C is the second order. Based from the graphs, we can see that the graph C has the most linear relationship between time and the reciprocal of the concentration of hydrogen iodide. Now, it is safe to say that the order of reaction is a second order reaction. Another approach is used for the determination of the order of reaction. The obtained values of concentration will be tested by its R-squared values. Mathematically, R-squared having a value closer to 1 means that the relationship between x and y values are linear. So how can we know the value of R-squared for each order of reaction? First, use the stat mode in your calculator, then use the a plus bx function. Next, input the value of time as your x values, then use the values of concentration as your y values. For zero order, use the concentration of hydrogen iodide for y values. For first order, use the natural logarithm of the concentration of hydrogen iodide as your y values. For second order, use the reciprocal of the concentration of hydrogen iodide as your y values. Next is to press AC, then press Shift plus Stat, then choose Reg from the choices. Then press the number corresponding to the letter R. Raise the R value to the second power to get the R squared. For zero order, the R squared is 0.8529. For the first order, it is 0.9621. And for the second order, it is 1. Based on the R squared, the highest value corresponds to the second order of reaction, which is the same answer obtained in the first approach. For the half-life of a reaction, presented on the screen is the process on how it was obtained. You can pause the video if you want to try getting it by yourself. To proceed, the half-life of a zero-order reaction is the initial concentration over 2K, where K is the rate constant. For the first-order half-life, it is equal to 0.693 or the natural logarithm of 2 over the rate constant. And lastly, for the second-order reaction, the half-life is equal to the reciprocal of the product of the rate constant and the initial concentration of the reactant. Now, let us proceed to the discussion of the collision model. The main idea for the collision model is that molecules must collide to react. It is based on the kinetic molecular theory, which states that the increase in temperature would cause the molecular speed to increase as well, and as the speed increases, the reactants are forced to collide more frequently. The greater the number of collisions occurring per second, the greater the reaction rate. And as the concentration of reactant molecules increases, therefore the number of collisions increases, leading to an increase in reaction rate. Now, for the orientation factor, it states that the relative orientation of a molecule during collision could determine whether the reaction will proceed or not. Take the illustration below as an example. The image above is an effective collision as it proceeds in the production of the product since the orientation between the reactants are favorable. Meanwhile, the illustration below is an example of ineffective collision as it did not produce the product due to the reactant's orientation. As shown in the screen is a graph. But what is this graph? This graph shows that the reactant must possess a certain energy for it to produce the product, which is the term we know as the activation energy. Activation energy is defined as the minimum energy required to initiate a chemical reaction. In the center of the figure, we can see an intermediate called an activated complex. Then, the state of the system at this point is often referred as the transition state. The activation energy is commonly used for determining the temperature dependence of the reaction rates. Rate constants of many chemical reactions vary with temperature in accordance with the expression K is equal to A times E raised to E sub A over RT. By taking its natural logarithm, the following expression will be obtained. Ln K is equal to negative E sub A over RT plus ln A, where K is the rate constant, E sub A is the activation energy, R is the universal gas constant, which is 8.314 joule per mole Kelvin, T is the temperature, and A is the Arrhenius constant. The activation energy can be determined by plotting 1 over temperature versus the ln of K. The slope of the graph represents the activation energy over the universal gas constant. Another way for determining the activation energy without graphing is with the help of two different values of K and T using the formula below. The formula is ln of K2 over K1 is equal to the quantity of negative E sub A over R multiplied by the quantity of 1 over T sub 2 minus 1 over T sub 1. Now that we know how to obtain the activation energy, we can use it to solve this problem. The problem is, what is the activation energy of the reaction given that the rate constant at 298 Kelvin is 3.46 times 10 raised to negative 5 per second, and the rate constant at 305 Kelvin is 9.63 times 10 raised to negative 5 per second. The formula to be used is ln K2 over K1 is equal to the quantity of negative E sub A over R multiplied by the quantity of 1 over T sub 2 minus 1 over T sub 1. You can pause the video to try solving it by yourself. The answer for the problem is E sub A is equal to 1.105 times 10 raised to 5 joule per mole or 110.5 kilojoule per mole.
So the next part is catalysis. Catalysis is a process that affects the reaction results of the catalyst. So the catalyst, on the other hand, is the reaction without soot or out. So the catalyst also lowers the activity for the reaction. So for this, there are different types that I will discuss. First is heterogeneous catalysis. Next is homogeneous catalysis and enzyme catalysis. So heterogeneous catalysis, the reactants are either gaseous or liquid, while the catalyst itself is solid. So the whole reaction for this catalysis takes place on the surface of the solid catalyst. So that's why it is also referred as surface catalysis. So for heterogeneous catalysis, the mechanisms is not really understood yet, but there are certain sites on the surface, and we call them active sites, and those active sites appear to be able to weaken or break down the reactants.
One example of heterogeneous catalysis is the hydrogenation of saturated organic compound. In this case, we use eth by a metal catalyst such as platinum or nickel. So here, the metal surface weakens the bond gas, and this phenomenon is called adsorption. The hydrogen molecules dissociate all hydrogen atoms, each of which is weakly bonded to a nickel atom, sweet. So these absorbed hydrogen atoms can move across the metal surface, and eventually they will combine with ethene, forming ethane reaction. So another type of catalysis is called catalysis. So from the word itself, it's one. So reactants and catalysts are both in one phase. So it is either on the gaseous phase or liquid. And one example of catalysis is the acid catalyzed addition of metic acid to form acetic acid. And this method shows us how the hydrogen ion is able to catalyze the reaction to form acetic acid. And last but not enzyme catalysis. So an enzyme is actually a catalyst is natural organism. So they are mostly plants. So for enzyme catalysis, some are actually homogeneous while some are also heterogeneous. And in this type of reaction, the reactant is substrate. So for enzyme catalysis, it is actually dependent on the pH level of the solution. And the catalyst works best at optimum pH, which ranges between 5 to 7 values. So this is an example of the mechanism for enzyme catalysis. So the reaction is in the active site as we part, and it is highly specific. And the substrate is initially bound to the active site via non-covalent reactions. And after the bond active site, multiple biochemical reactions can speed up the fermentation process. And that's it for our discussion about this. Thank you so much for staying with us for our presentation. Once again, this is Terbium. Have a good